What's up, gamers? We are going to be talking about end behavior of functions today, and we're going to also talk about this really sweet thing in math called a limit. And a long time ago, like 16, no, not 16 years, a while ago though, when I was in high school, when I was just a young, naive student like you guys, I had a pre-cal book that said pre-calculus with limits on it. And I thought that was the most absurd thing. Why was my teacher limiting my growth like this? You know, I want to be unbounded. I want to be limitless. It wasn't until I went to college that I found out that limit is actually a math term. And I became way less disappointed with the title of that book. But we're going to talk about limits today. These are going to be pivotal, paramount, probably one of the most important things you learn in calculus. Today we're just going to talk about the easy baby version and talk about the end behavior of functions. We're not going to talk about limits everywhere, just at the ends. All right. So let's start by developing this idea of what a limit is. So the best definition I can come up with that's not needlessly mathy, right? Because I hate to just beat you guys to death with math definitions that are overly formal and don't make any sense. The best one I can come up with for a limit is sorry, I can't even read my own writing. What value a function heads towards as the input gets close to a specified value. And you're going to say, Barton, if this is the dumbed down version, I don't even want to see the real version. But all this means is where are we going? What are we heading towards? What's our end goal with our function? Okay. And I'm going to give you an example in a second, but let's read the second definition, okay? So the end behavior, this is kind of just a special limit. The end behavior is a limit where the input is the highest and the lowest value in the domain. So this means whatever the biggest number you're allowed to plug in, it's that number. And whatever the smallest or most negative number you're allowed to plug in is what happens over there too. So let's maybe take a second and look at maybe a boring function, but an interesting one. Okay, let's look at y equals 2 to the power of x. You might not know how to graph this yet, so I'll do it for us. This is an exponential, and what it looks like is this. There is an invisible thing called an asymptote right here on the x-axis, and that's just an invisible line this graph is going to get really, really close to, but not touch it. Right? It'll get right up next to it, really uncomfortably in its face, but it won't ever touch it, right? It's like when you were little and your brother or sister would stick their finger an inch from your eyeball and say, "I'm not touching you." Okay, you're not touching me, but you're in my bubble, dude. So let's investigate this function, and then we'll talk about a limit, right? So I'm going to go ahead and just tell you a couple values. My go-tos are always -2, -1, 0, 1, 2. And then we'll figure out what our y's are. So if I plug 2 in, 2 squared is 4. Good job. You guys have known that since probably first grade, second grade, I don't know. All right, 2 to the power of 1 is just 2. Anything to the power of 1 is itself. So this is 2. Anything to the power of 0, except 0, is 1. Now let's refresh negative exponents real quick. If I have 2 to the -1 power, what that means is this negative takes the base and the exponent and moves it to the other side of the fraction. So this is 1 over 2 to the first power. So this is just 1/2. It's basically the reciprocal of the positive exponent. So using that pattern, if it's the reciprocal of the positive one, it's just 1/4. Okay, so we haven't really talked about the limit yet, right? Let's go re-look at our definition. So it says what value a function heads towards as the input gets close to a specified value. And for the end behavior, that specified value is the highest and lowest or most negative, I kind of use those words interchangeably, value in the domain. So those are the biggest numbers we're allowed to plug into this, and the smallest numbers we're allowed to plug into this. So if we look at the graph, there's arrows here. That means it keeps going. So could you do 2 to the 5th power? Yeah, you could do 2 times 2 times 2 times, right? 2, 4, 8, 16, 32, right? Oops, 32. And I'm going to say, well, could you do 2 to the 50th power? I don't know what that number is, but obviously you could write 52s and then multiply them together if you were patient. And you could do 2 to the 500th power, and you could do 2 to the 5, and then whatever this number is, power, right? There's not a limit here. There's not or I should be careful with the words I use. There's not a boundary that stops me. I could take as many 2's as I want and multiply them together. So the domain of this function, it goes all the way up to infinity. The domain for x, the values for x I can plug in are up to infinity, parenthesis because we can't get there. And then likewise, I could plug in any negative number I want. The negative numbers are basically just telling me to do, if I have 2 to the negative 5th power, that's 1/2 times 1/2 times 1/2 times 1/2, and it keeps going forever, right? I could put negative 50 or negative that number and do this if I were patient enough or had a nice enough calculator, right? So the x's I can plug in go up to infinity and down to negative infinity. There's no limit to the numbers I can plug in. So what we want to know is, what do I go towards, or what's the behavior at the end? What happens if I plug infinity in? What happens if I plug in negative infinity? And here we're going to just look at the graph. Okay, if I go negative, this graph gets really, really close to the asymptote, and the asymptote's on y equals 0. So what that means is that this graph is going to get really close to being 0. Obviously, if you take 1/2 times 1/2 times 1/2 times 1/2, this is 1/16. And if you did this, I'm not going to guess that one, but if you did this one, it's probably like 1 over like a really big number, but it's not 0, right? It's never going to get to 0 because it's an asymptote, and you can't get to the asymptote. You never quite reach it. So we would say the limit, or the end behavior here, is as, I'm going to write this out in words. Let's change the color. Come on, change the color. As x goes to negative infinity, y approaches, right? It gets really close to 0. So this would be our limit. The limit as x gets to negative infinity is 0. And there's a way you could write that in math. The limit as x approaches negative infinity equals 0. I forget my calculus. Maybe you're supposed to put y there. The limit of y as x approaches negative infinity. Anyway. Likewise, as x goes to infinity, as this exponent gets bigger and bigger and bigger, this number just explodes and goes up really far. So likewise, we can say that the end behavior on the right side, or the positive side, is y goes to infinity as well. Okay? So this idea is just, if I keep going as far as I can, what happens to the function? Does it go towards a specific value like 0? Or does it just diverge and go up forever, maybe down forever, or wiggle forever in some cases? Okay. This is very abstract, and this is not on your homework. This is just me trying to help you get a bite into what a limit is. This is going to be your calculus teacher's problem later. I'm just trying to help you get an idea of what we're asking so you know what question you're even answering. Okay. So let's look at this wonderful example. And the way you're going to probably see the limits on your homework is something more like, as x approaches, and they're going to leave you a little space here to fill in a number, f of x approaches something else. They don't use the proper calculus limit notation, and that's okay. It's just notation, right? It doesn't matter how I write it. It's what I write that's important. Okay, so if we look at this radical, we want to know the end behavior. So the end behavior means how far left do I go and how far right do I go, and what happens at the ends of those things. So let's start with the left side. Because this is a radical, it has a vertex and a starting point. It doesn't go left forever like my exponential does here. It stops right here. So we're going to say as x goes to -2, because that's my smallest domain value. Now I want to know, what is f of x? And this is just a fancy way for mathematicians to write y. So when I get to -2, or maybe I just get close to -2, what y value do I get really close to having? So if we look, when I'm at -2 on this, I'm at, and it's not labeled here, but this is 1. So I'm at 1. There you go. Now on the other end, we need to know the right side as well as the left side. In this exponential, or I'm sorry, I misspoke. In this radical, radicals continue on in one direction forever. The domain of this is bracket -2 to infinity, right? Because we touch the -2 that's defined there, but it goes to the right forever. That's our domain. So our other number, as x approaches, is infinity, because it goes right forever. So if this thing keeps going, what y value is it getting to? For square roots or radical functions, this continues up forever. The bigger number I plug into x, the bigger the y value gets. It's never going to level off. It keeps getting bigger forever. So we say that it's divergent. That's a nice word to say. It goes up to infinity. Okay, and this is pretty much the gist of what you need to know for end behavior. Okay. For your homework, you are going to mostly be looking at polynomials. Again, if you're not in my class, like if you're some kid in like New York, I don't know why you're watching an Arizona teacher, because your teachers are probably way better than me anyway. But if you're some kid in New York, this might not be true. But for my students in Arizona, the like 48th worst state for education, you know, you kind of want to, you know, put some limits on what our homework is. So for your homework, we're only going to look at polynomials, even though these non-polynomial questions are way more interesting. Okay, so for polynomials, there is thankfully a wonderful pattern that keeps you from having to graph things every time and plug in values excessively. There's a pattern that we can take advantage of so that we don't have to stress ourselves out about end behavior. Okay, so the end behavior of a polynomial is determined by two things. Those two things are the leading coefficient and the degree of the polynomial. So both of these things, you need to have your polynomial in standard form, meaning the exponents go in descending order. So they start at the biggest and get smaller as we move through the polynomial. As long as you have that, the only thing you actually care about for end behavior, the rest of the stuff does stuff, but for end behavior, the only thing you care about is this number right here in the front and that exponent right there. The exponent is the degree, meaning what's the biggest exponent in the polynomial. And then the leading coefficient is the coefficient in front of the biggest term, as long as it's written in standard form. Okay, so these two things do two different things, but they make our life pretty easy. Okay, the first thing you need to know is that the leading coefficient, here, I'm not even going to write the whole word. This isn't English class. I don't have to write words. Leading coefficient determines, and you should be writing this down if you're not, the right sides, yeah, there we go, end behavior, this thing right there. But I'm abbreviating because I'm a lazy math teacher. Okay, so our leading coefficient determines the end behavior of the right side. So that means as x goes towards infinity. Polynomials all have a domain of -infinity to infinity, or all real numbers, whichever way you prefer to say it. But because polynomials always have the same domain, these are always going to be your x values. So this leading coefficient is telling us when I go to the right really, really far, it'll tell me what happens. So here's what you're checking for. Is it positive or is it negative? If it's positive, that means that your end behavior on the right side will go to positive infinity. And if it's negative, it means it's going to go to negative infinity. And if you don't believe me, I'm going to do the cop-out math teacher thing. I'm going to say go plug in numbers and check it for yourself. Like make up your own polynomial and then use a calculator to plug in like 10,000 and just see what happens. And it'll become pretty obvious why. But the thing is, exponents matter so much more than leading coefficients that it just makes this term overpower everything else. So if this is going to be positive, it doesn't matter what this stuff is. It's going to be positive, right? Like, even if you have 50 negative things, if you have 10 trillion positive things, they're not going to cancel out. Same thing with the negative. If this term ends up negative, then this will always be negative. Okay. Now let's talk about the degree. The degree, or your largest exponent, will tell you what the left side does. Tells you the left side. And we can put end behavior just to be complete there. And what it's going to do is it's going to tell you, does it match or does it differ from the right side? So the way you tell that is you are looking, is the degree even or odd? Okay. If it is even, the left is going to match the right. If this exponent is odd, then the left is different. Different. Again, I'm a math teacher. I've got a master's degree. I can write, just not spell. Okay, so one more time. Leading coefficient tells us the right side. If the leading coefficient is positive, it's going to go to positive infinity. If it's negative, it's going to go to negative infinity. Then we look at the largest exponent and ask, is it even or odd? If it's even, the left side is going to match the right side. So for this one, it would go to positive infinity on the right side, because 2 is positive. And because this is odd, it's going to do the opposite. So ours would go to negative infinity. But if it was even, it would go to the same one. It would go to positive infinity. Okay, let's go look at 4 examples really quickly because they're so straightforward and easy. Your homework is going to take you 5 minutes. Okay, because these are polynomials, they all have the same domain. So the 2 x values we're looking at for this entire page, because they're polynomials, are negative infinity and positive infinity. There we go. Let me just finish copying this. If I were a professional, I would have, filled these in ahead of time, but then you wouldn't get to listen to my melodious voice. Okay. So we are going to start with a positive infinity because the first thing I want to check is this leading coefficient. Because there's a negative sign here, this is negative. We don't need the number even though it's an invisible 1. So because our leading coefficient is negative, as x goes to the right, it's also going to go down to negative infinity. Okay. Now we check the degree of the polynomial. We look at our largest exponent and we ask, is it even or odd? Because 3 is an odd number, that means that our end behaviors are going to be different. The right side is going to go down, the left side is going to go up. So this is going to go to positive infinity. All right, next question. We look at the leading coefficient and ask, is it positive or negative? 9 is a positive number, so that means on the right side, my graph is going to go up to a positive number to positive infinity. And it'll just keep increasing forever. The bigger number you put into x, the bigger number you get for g of x. Now to check the end behavior of the left side, we look at the largest exponent, and we ask, is it even or odd? And 8 is an even number because it's divisible by 2. Even means the end behaviors match, so the left side is also going to go up to positive infinity. All right. Here, I threw in some really just weird numbers, right? 99, such a bizarre number. You know, is it a 9 or is it 2 9s? But we're going to start with just asking, is it positive or negative? We don't care what the number is. It could be 3.14. It could be actually pi, because 3.14 is just a rounding. So this is positive. That means our limit, or our end behavior, as x goes to the right forever, it also will go up forever to positive infinity, because this is positive. Then we check our exponent, ask is it even or odd? It's odd. So that means the end behaviors will be different. So when the right side goes up, the left side will go down to negative infinity. Last one. Again, don't freak out because this is a decimal. It doesn't matter. You don't care what the number is. You care about that negative sign. So, ooh, actually, look at this. Mr. Barn laid a trap for us. 88, 90. This question isn't in standard form. So, you need to be aware of that, right? Sometimes this will happen where they'll put it not in standard form to mess you up. We don't care about this. It's not the first. Come on, you gosh darn son of a gun. God bless America. Okay. We don't care about this. We only care about the leading coefficient and the largest exponent. Because this is not the largest exponent, it's not the leading coefficient. The leading coefficient is referring to this number right here. So we look, this actual leading coefficient is negative, so that means as we go to the right on our function, it's going to go down. So this is going to go to negative infinity. Now we look at our real largest exponent. This is even, so that means our end behaviors must match, and this is also negative infinity. All right. Hopefully that's not too convoluted for you. That's end behavior. Luckily, you only have to know polynomials for right now. So go ahead, get comfortable with that. If you need help, look up another YouTube video if I'm not your teacher. If I am your teacher, email me, hit me up on Band, send me a carrier pigeon, use quantum entanglement to send me messages. That'd be tight. All right, I'll see you next video. Don't forget to like, comment, subscribe. Let me know what you thought about this video in the band messages. See you guys later.